stopped. Velocity 0. Don't need a sign term. Particle changes direction. Velocity changes signs. Has to be said. And then how do you find it? Sign turn again. Speed. A couple different things. Speed is the absolute value of velocity. But then if they ask you is something speeding up or slowing down, speeding up is when velocity and acceleration have the same signs. Slowing down, opposite signs. Distance traveled versus new position. This is huge. Distance traveled. Remember, distance can never be negative, so it's absolute value of velocity, but it's area under the curve. Okay? If you're doing distance traveled with a calculator, just plug in the absolute value sign behind the integral. If you're doing it on a graph or by hand, you have to split it up. New position is starting position plus net change. Okay, all that you need to know cold. It's very, very, very common. Okay? So if you're able to graph it, or if they give you a graph and this is velocity, okay, then what's going on in this graph? Okay, velocity positive, all of this is particle moving right. Velocity negative, this is particle moving left. Okay? Particle stopped is here, here, here. Particle changes directions is just here. Okay? Now let's do speed. Speeding up, speed is the absolute value of velocity. So the speed here is 3. And then down here, the velocity would be -2, but the speed is 2. So this is speeding up because you go from 0 to 3. This is speeding up because you go from 0 to 2. So going away from 0, speeding up. Going away from 0, speeding up. Slowing down, going towards 0. Going towards 0. Okay? Speeding up, one more time, more formally, or increasing speed, whatever. Speeding up is when velocity and acceleration have the same sign. Well, let's look at that again. Let's start with the velocity. Okay? If this is a velocity graph, then velocity is positive above 0. So this is velocity positive, this is velocity positive, this is velocity negative, this is velocity negative. Now let's do the same thing with acceleration. If this is a velocity graph, acceleration is the derivative, so it's the slope. So let's find the sign of our acceleration. Well, in this region, slope is positive. In this region, slope is negative. This region, slope is negative. This region, slope is positive. So, to reiterate, speeding up is where they have the same signs. So speeding up is going to be right here, plus plus, and right here, minus minus. Speeding up, going away from 0, or velocity and acceleration have the same sign. We can't say going away from 0, it's not formal enough. Slowing down would be, again, velocity and acceleration have different signs. Okay, tangents. Where does f of x have a vertical or horizontal tangent? Okay, that tangents, that's having to do with slope. Horizontal tangent has a slope of 0. Vertical tangent has a slope that's undefined. So, since it has to do with slope, you find the derivative, or maybe they gave you the derivative. If the derivative was given, like this guy, if this was my derivative, the horizontal tangent would be when the derivative is 0, which is going to be when the numerator is 0, x equals -2. Vertical tangent would be when the denominator is 0, because that's when this would be undefined, and that would be x of 3. So horizontal tangent, vertical tangent. But again, that's only if you already have the derivative. If you don't have the derivative, you find it first. Okay, asymptotes. Horizontal asymptote is the same as asking what's the limit on the right side and the left side of your graph. So for example, okay, let's say we have a graph that goes like this. Okay, I'd say, assuming this is f of x, I'd say the limit of f of x as x approaches infinity, which means on the right, okay, what is the height? And that would be 2. Okay, remember, limit just means height you're approaching. On the left side, the limit of f of x as x approaches -2 negative infinity would be -3. Okay, so horizontal asymptotes is the same as saying what is the limit at positive infinity and at negative infinity. Now you also have your old Algebra 2 rules, which are sometimes easier. Okay, if I asked for horizontal asymptotes for this, that's the same as the limit at infinity and the limit at negative infinity. But you might remember from Algebra 2, if the degrees are the same, it's just the coefficients in front. Okay, so that both of these would just give 3/5, one horizontal asymptote. If the degree on the bottom is higher, okay, then it's 0. But the reason is, okay, if I plug in infinity, and remember these guys don't really affect it as much, you pop out the highest degree terms and simplify it, and then plug in your infinity and your negative infinity. Okay? If I plug infinity right now, if I plug in infinity, you get infinity on the bottom, which is 0. If I plug in negative infinity right here, that would be a negative value, and you get 3 over negative infinity, but that still goes to 0. Okay? Horizontal asymptotes. Now, vertical asymptotes. Vertical asymptotes would be when your denominator is 0, but it doesn't cancel with another factor. And this isn't really all that common, honestly. So right here at 3, that's not a vertical asymptote. That's a hole in the graph. That would be the limit of f of x as x approaches 3. Okay, there's a hole there. So you cancel and then plug in the 3, you'd get 1/5. Okay. Vertical asymptote, though, would occur when x is -2. Because that one doesn't cancel, so it's a vertical asymptote. Okay? Similarly, if I said, what is the limit as x approaches -2? Since there's a vertical asymptote there, if there's a vertical asymptote and your graph is approaching a vertical asymptote from whatever side it's approaching, as I approach that asymptote, the height is going to go to either infinity or negative infinity. So since you know it's either infinity or negative infinity, you can technically say that does not exist because you can't actually reach that. Now, if they ask you to specify one or the other, then you plug in a number really close to -2, like -1.9 or -2.1, depending on if they say left or right. Okay, continuity. This one's not super common, but if you have to prove that something's continuous, then you say the limit from the left. Let's say this one has a hole at 1, 5. So the limit as x approaches 1 from the left is currently 5. But to be continuous, that has to equal the limit as x approaches 1 from the right. That's also 5, but this is still not continuous. Right now the limit exists because the left and right hand limits are the same, and the limit as x approaches 1 is 5, but that doesn't make it continuous. To make it continuous, we have to fill that hole. So the final piece of the continuity definition is it has to also equal f of 1, which is 5. Okay, 3-part definition for continuity. Okay, let's talk a little bit more about limits and continuity. Okay, is the function, well, I got to get some numbers in here. 1, 2, 3, 4, 5, 6, 7, 8, -1. Okay, is this function continuous everywhere? If not, say where it's not continuous. Well, it's not continuous at 3, and it's not continuous at -1. Okay, does the limit exist everywhere? The limit does exist at 3, and the value of the limit is the height of the hole. The limit as x approaches 3 is the height it approaches from both sides. So the limit would be the height of the hole. Let's say that's 2. Okay? Now, what is f of 3? That would be the point 3. Okay? And that is why it's not continuous. Those two things aren't the same. But don't confuse that with limits. The limit does exist. It's 2. It's the height of the hole, and it's typically a hole for a limit. Okay? Now let's talk about right here. 1, 2, 3, 4, 5, 6, 7. Okay, the limit as x approaches 7 is still the height, whatever we think that height is. Let's call it -1. Okay? Is it continuous here? Yup, because the limit exists and it is also equal to the value of the function. It's a solid point. Okay? How about over here at -1? The limit as x approaches -1 does not exist. dne. And that's because the left-hand limit doesn't equal the right-hand limit. And you'd have to write that. Left-hand limit doesn't equal right-hand limit. Okay? The limit doesn't exist, and it's also not continuous. Now let's compare that to differentiability. To be differentiable, the function has to be continuous, and it has to be smooth and curvy, no sharp points. So this is differentiable everywhere except for, remember this point is right here, and right here where the graph is broken. Okay? It's differentiable everywhere else. So right here, the derivative does not exist, and here the derivative does not exist. The last type question where the derivative won't exist is if you have a vertical tangent. So right there, that also does not exist. Okay? So differentiable has to be smooth and curvy, can't have a sharp point, can't be broken, and can't be a vertical tangent. Everywhere else, this is differentiable. Now, if they ask you to show or state why something's not differentiable at a sharp point, they had that one year for free response, and they actually accepted because there was a sharp point. But the real reason is you're supposed to say the derivative from the left doesn't equal the derivative on the right.